We are now quite familiar with the concept of a category. A category has objects and it has arrows, and there's a composition rule for arrows. The next concept in category theory is that of a functor. So let me give you the definition of a functor. A functor F. So now a functor relates to categories C and D. So what this notation means is that F is a functor from category C to category D. Associates. So first thing it does is to each object C of C, it associates an object FC of D. And the second thing it does is to each arrow let's say F in C, and if you have any two objects A, B, it associates an arrow F of F, which is an arrow in the category D, and it goes from the object F of A to F of B. And these two pieces of data must satisfy the following axioms. Basically, these axioms say that they must preserve the categories' structures. So the first is that for every object A of C, F of identity of A. So remember, each object has an arrow from itself to itself, which is called the identity arrow, and this should be the identity arrow of F of A. And the second is the composition axiom. So this is called the identity axiom. And the second is the composition axiom, which says that for arrows, so suppose you have A, B, and C, three objects in the category C, and you have arrows F and G in C. F of G circle F should be F of G circle F of F. This is called the composition axiom. Okay, so basically a functor from one category to another is defined on two levels. It's defined on the level of objects and on the level of arrows. And on the level of arrows, it needs to satisfy two properties. It should take an identity arrow to the identity arrow of the corresponding object, and it should preserve composition of arrows. Let's look at some examples. So let K be a field, and let's write vec K the category of all vector spaces over K. So remember, in this category the objects are vector spaces over K, and given two vector spaces V and W, the arrows from V to W are all the K linear transformations from V to W. Now for any object V of vec K, define its dual, which we denote by V prime, to be the set of arrows from V to K itself. So K is a vector space over K. It's a one-dimensional vector space, and we just take all the arrows from V to K, which in other words is just the linear maps from V to K, or which we also call linear functionals on V. Now I'll define a functor which I'll denote D from vec K to vec K op. So let me remind you, if you have a category C, you also have a category C op associated to it, which is called the opposite category. And its objects are the same as the objects of C, but the morphisms are reversed. So the arrows from B to A in the opposite category are by definition the arrows from A to B in the original category. And composition is also reversed. So F circle G in C is G circle F in C op. And this makes sense because of the way that arrows are defined by reversing the directions of the arrows. So now we are going to define a category, a functor from the category vec K to its opposite category. Such a functor is sometimes called a contravariant functor when it goes to the opposite of another category. But in any case, let's go on with the definition as follows. So now firstly I need to define the functor at the level of vector spaces. So I need to say what is D of a vector space. So D of V is going to just be V dual. And then I need to define what D is on the level of arrows. And so what I need to say is what is D of F. So maybe let's just say for each F from a vector space V to a vector space W, suppose you have a linear K-linear map F, then I need to define df. So that should go from W dual to V dual, not from V dual to W dual, because it's a functor to the opposite category. So this would be vec op of V prime comma W prime, but then it is just a linear map from W prime to V prime. So we'll define this by the following equation, df. So now it should take a linear functional in W. So let's say xi, where xi is a linear functional on W, and it should give me a linear functional on V. And there's only one way to put these three symbols f, z and V together, and it is to say fv. So that's the definition of df from W prime to V prime. And now we need to check that this is a functor. So let's check the axioms. So the first thing I need to check is whether D takes the identity to identity. So let's look at D of identity of so now we have let's say identity of V. V is a vector space, so D of identity of V. So identity of V is from V to V, and D of identity V is from V prime to V prime. And so we need to say what it does to Z prime in V prime. Maybe here I should say for all V in V, Z in W prime. Okay, so this evaluated at a vector V. Now Z is in V prime, and this is just going to be Z of identity of V, which is going to be Z of V. So that means that D of identity V is equal to identity of V prime, because it's taking Z, the linear functional Z is going to the linear functional Z. Okay, so that checks axiom A. And let's check axiom B, which is by far the most interesting part here. So let's look at, suppose we have arrows V, W, U, let's call them F and G. What we want to check is whether D of G circle D of F is equal to D of G circle F. So let's look at D of G circle D of F, and let's apply it to so we have like U prime. So we have dg goes from U prime to V prime, and df goes from U prime to W prime, and df goes from W prime to V prime. That's how the arrow reversing property of D works, right? So let's look at dg circle df, but this is the composition in the category vec op, right? And that by definition of the opposite category is df circle dg, and this is the composition in vec. Okay, so let's now apply this to some linear functional psi, and then let's see how it evaluates on a vector V. Okay, so by definition this is dg psi evaluated at f of V. But that is the same as psi evaluated at G circle F of V, again by applying the definition of D. But that is by definition the same as psi D G circle F psi evaluated at V. And so we conclude that dg circle df is dg circle f, and hence D is a functor. This D is an example of an arrow reversing direction. It's a functor from vector spaces to the opposite category of vector spaces. So it reverses arrows, and it's called a contravariant functor. Okay, so let me just define covariant and contravariant functors. So this is just a notational thing. A contravariant functor sometimes a functor from a category C to D op is called a contravariant functor from the category C to D. Okay, so instead of saying that it's a functor from C to D op, we'd say it's a contravariant functor from C to D. So this functor capital D that we defined earlier, this is a contravariant functor from vec K to vec K. Or you can just say it's a functor from vec K to vec K op. That's the notion of contravariance. Now let's look at more examples of functors. So let R be a ring and S be a subring of R. Now let R mod denote the category of R modules. So an R module, recall, is just an additive abelian group together with an operation from R cross M to M, which takes R comma M to R dot M, and this satisfies some nice properties which relate the ring structure on R to the abelian group structure on M. So you can review this in Algebra 1. So you have the category of all R modules. The objects are R modules, and arrows between two R modules are R module homomorphisms. And we'll say S mod for the category of S modules. Now the thing is, an R module can be thought of as an S module because S is a subring of R. So you can just take the operation from R cross M to M, which defines the R module structure on M, and then you restrict it. So you have S sitting inside R. So S mod M is sitting inside R mod M, and so this is a subset here, and you just restrict it, and you get an action of S on M. And so an R module is automatically an S module, and this is called the restriction of structure. So we have a functor res R mod to S mod. It's called the restriction functor. Is defined by res of M is equal to M, but now thought of as an S module. And res of F is equal to F. Now if F is an R module homomorphism from M to N, that just means that F of R dot M is R dot F of M for all R in R. But since S is a subset of M, if this is true for all R in R, this is also true for all R in S. And so F is also an S module homomorphism. So every R module homomorphism is an S module homomorphism, and so you can just define, but now this is thought of as an S module homomorphism. And this is the restriction functor from the category of R modules to the category of S modules. Let's look at a very simple example of a functor. Let C be any category. Then define a functor from C to C, which is called the identity functor. It is defined by setting identity C of C is equal to C for every object C of C, and identity C of F is equal to F for every arrow in C. And it's very easy to check that this actually satisfies the axioms in the definition of a functor. This is called the identity functor, and this suggests that we can view categories themselves as forming a category. The objects of this category of categories are categories. The arrows in the category of categories are functors from one category to another, and we've just constructed the identity arrow from each category to itself. However, you need to be a little careful here. You could run into set theoretic issues related to Russell's paradox. Okay, let's look at one more example. So now let C be any category whose objects are sets and arrows are functions, and the composition of arrows is composition of functions. So I'll just say any category whose objects are sets, arrows are functions, and composition is composition. Composition of functions. So we've seen lots of examples of this, and most categories that we study in algebra or topology are of this form. So for example, we have the category of groups, we have the category of sets, we have the category of rings, we have the category of topological spaces where arrows are continuous functions, and so on. Okay, then define a functor which from C, maybe I'll give it a name, I'll call it omega of C. It's from C to the category of sets, which takes for every object C the underlying set C. So C a priori is an object of the category C, but I just stipulated that every object of the category C should be a set. And omega C of F is the underlying function, the function underlying F. Okay, more explicitly, if F is an arrow from C to D, it's an arrow in the category C, then this F is actually a function from the set C to the set D. And this functor omega is called the forgetful functor. Now the idea is that the category C, its objects are sets, but they are sets with some additional structure. So for example, if C were the category of groups, then the category C is the category of sets together with the additional structure that is the binary operation on the group. And this must of course satisfy some axioms and so on. And what this functor omega C does is it forgets all that additional structure and only remembers the fact that you have a set. Okay, this functor has many beautiful applications. We may see some in a later lecture. But for now, it's just a nice example of a functor. Okay, I'll let you check that this is actually a functor. The next example, consider a category C. With a mild technical assumption, we require that the collection of arrows between any two objects is a set. This is not a very restrictive condition. All the categories of the form that we studied in the previous example, namely categories where objects are sets and arrows are functions, would satisfy this axiom. And unless you really worry about the intricacies of set theory, I would say not to pay much attention to this as of now. Now fix an object A of C. Now with respect to this object, fixed object A, I will define two functors from C to sets. So the first functor I'll denote by F subscript A, it's from C to sets, and the second functor is F superscript A. It is also from C to sets, but it's a contravariant functor, so I'll call it as a functor from C to the opposite category of sets, as follows. So firstly I'll define F subscript A. So F subscript A of B is defined to be all the arrows from A to B, and I need to define it on the level of arrows. So suppose now I have B to C, I have F, then so this should be a function from CAB to CAC. This is FA of B, this is FA of C. So I need to define a function from FA of B to FA of C. So if I have arrow G from A to B, I need to somehow construct an arrow from A to C, and there's only one way to do that, which is to take F circle G. And similarly we'll define F superscript A. It's sort of the dual notion, so we are just going to reverse the arrows, and F superscript A of F. So now this is going to be C from so now F is from B to C as before, and then we have from C. Now because it's going to the opposite category, this will be from CA to CBA, which means that now we are given something from C to A, we need to construct something from B to A, and there's only one way to do that, which is to take G circle F. So this is defined by FAF of G is G circle F. Now we need to check that these are functors. Of course, I've defined them on the level of objects, and I've defined them on the level of arrows. Just as an exercise, let's check that one of them satisfies the axiom sort of functor. I'll leave the other for you to do yourselves. So let's check that F superscript A satisfies the conditions A and B in the definition of a functor. So the condition A was that the identity arrow goes to the identity arrow. So so F superscript A of the identity of B, we have some element B, so now we have the situation. And we have G here, and so this is by definition G circle identity of B, and so this is G, which means that F circle A of the identity of B is the identity function of the set B to A, which is the identity function of F superscript A of B, and that is the identity axiom. So FA satisfies the axiom A, and let's check that FA satisfies the axiom B. So now the thing gets a little more complicated. We have B to C to D, we have 3 objects, and we have 2 morphisms. Let's call them F and G, and now we have H from D to A. So let's look at what is FA of G circle H a G circle F evaluated at H? Well, this is by definition H circle G circle F. But by associativity of composition, I can write this as H circle G circle F. That is FA F applied to H circle G. And so that is FAF applied to H applied to G. But this is composition in sets, in the category set. And so in the category set op, this is the composition of functions. So in the category set op, this is this is G applied to H. And this is composition in the category set op. And so what we have is FA G circle F is FA G circle FA F. So F superscript A is indeed a functor. I'll leave it as an exercise and I would highly recommend it that you sit down and write down a careful proof that F lower A is also a functor. Now, one last example of functor. We look at categories with one object. So let C and D be categories with single objects. Let's say C and D respectively. So the category C has a single object which I denote by C, and the category script D has a single object which I denote by ordinary D. And let MC denote the set of arrows from C to C, and let MD denote the set of arrows from D to D. Okay, and what we've seen is that these are actually just monoids, because the definition of a category says that this set comes with a composition operation and an identity. So these are monoids. And a functor F from C to D must satisfy, there's only one object, so it must take this object to the only object of D. And so the only question is, what does it do on arrows? So what we get is F gives rise to a function F, which I'll also denote F from MC to MD, which is just F goes to, yeah, maybe I'll call it small m goes to F of m. And this function must satisfy the axioms for a category, which is that F of identity of C, which is the identity of the monoid MC, is the identity of D, which is the identity of the monoid MD. And the second is that F of M1, M2 is equal to F of M1, F of M2. So what we are saying is that F is a monoid homomorphism. So functors between single object categories are homomorphisms of the corresponding monoid. If these categories, if these monoids were actually groups, then they would be group homomorphisms.